In this paper, we propose a principal approach to guide data collection via factor scaling curves. Imitation learning policies usually perform well in nominal environments, which are similar to the training distribution. However, you usually struggle to generalize to different environments with factor variations, for example, distractor, table texture, and lighting. This brings us to the central question. In order to improve the policy generalization, what kind of data should we further collect? The first option is to greedily cut data for the worst factor. However, this overlooks factor intrinsic difficulty and effect on other factors, thus leading to only marginal improvement. The second option is to equally cut data for other factors, which is not efficient because it fails to prioritize important factors for which data collection improves the most performance. The third option is to prioritize factors that can lead to the greatest overall improvement. But how do we choose the correct factor to prioritize? To answer this, we propose factor scaling curves, which can predict the effect of adding data for a specific factor on the policy performance, and prioritize factors for greatest potential improvement for data collection. The first step of constructing a factor scaling curve is to train policies with different number of data for a specific factor and plot their performance. The performance metric can be a policy success rate from real robot evaluations or proxy metrics like embedded similarity. The second step is to fit a power law curve based on this point and predict the expected policy performance given the data budget. Then, we repeat the same steps for other factors and obtain the expected improvement for each factor. And we just need to pick the factor with the highest expected improvement to collect data for. We evaluate our method on several challenging real-world tasks, including put tomato in plate, fold towel, and put mouse in drawer. We evaluate our method in both training from scratch settings using diffusion policy, and fine-tuning VRA settings using Pi0. Our method is able to effectively solve this task even on a combination of environment factor variations, such as robot pose, object pose, and table texture. One benefit of our method is that it can accurately predict the policy performance improvement. In the fold tile task, the fitted curve can accurately predict the policy performance trained with additional factor data. It also correctly prioritizes the camera pose and distractor factor variation to collect data for, beating the baselines. The same conclusion also holds for other tasks. For example, in the put mouse in drawer task, the predicted performance of our method is 66%, closely matching the actual policy performance trained on the extra data collected using our method. Meanwhile, our method beats the equal baseline by a large margin. The second benefit of FSC is that it enables efficient data collection in long horizon, dexterous manipulation tasks. We compare our method with baselines that equally cut data, greedily cut data for the worst factor, and remix. Our method consistently outperforms all the baselines across all the tasks. We further show that constructing factor scaling curves with proxy matrices like embedded similarity maintains near equal performance in guiding data collection. This creates an extremely lightweight version of our method by eliminating real robot evaluation requirements. In summary, we propose factor scaling curves which can model policy performance with factor data and guide data collection. We show the proposed method can effectively solve challenging real-world tasks. Furthermore, constructing factor scaling curves with embedded similarity preserves almost the same effectiveness in guiding data collection, while not requiring any hardware evaluation. For more results and analysis, please refer to our paper. Thank you.